Hello students, in today's class we will continue with where we left off in last class. So, we talked about minimum deviation and maximum deviation and the conditions in the case of Prism, and so today we will start with this concept called condition for no emergence. Condition for no emergence. So, what this basically means is we are going to write a condition for which a light ray which is incident on the prism is not going to emerge at all, right. So, which means if I consider a prism like this, so having an angle of refraction of some A, angle of prism is some A. So, we need to write a condition such that a light ray which is incident from here, a light ray which is incident on this face is not going to come out of this face, right. So, when will a light ray not come out of this surface? If TIR takes place at that surface, correct. So, we are going to write the condition for that. Now, keep in mind here I am writing the condition for no emergence. It means that any light ray which is incident on this surface after entering should get reflected. So, none of the light rays should come out of the prism. So, if you consider a light ray like this or like this or like this. So, if you consider any light ray after entering, so each and every one of these light rays should get reflected back. So, should undergo TIR. Now, we already have discussed about this in TIR. So, when I have to write a condition similar to that, I don't have to write the condition for each and every ray which is present here. I will have to choose one particular ray in such a way that if I write the condition for that ray, then each and every other ray will get reflected back also. So, let us try to understand that. So, let us say if this light ray enters into this medium, strikes here, and this is the angle of incidence for the second surface. Let me call this as R1 and this one as R2. So, we now know that we can say that if you look at this particular light ray which is incident on the second surface, can I say if this R2 is the smallest possible value. So, a ray which strikes the second surface with the smallest possible angle of incidence, so I am going to consider that particular ray which is going to be incident on this second surface at the smallest angle of incidence. Now, why am I considering that ray? Because if that ray undergoes TIR, then any other ray will also undergo TIR. Clear? So, that is the concept which we are going to use. So, out of all the light rays which are incident on this surface, I am going to choose that particular ray which strikes the second surface at the smallest angle. Clear? So, if that ray is getting reflected back, even the light ray which is striking at the smallest possible angle is getting reflected back, can I say that every other light ray which strikes at a larger angle of incidence will definitely get reflected back, correct? So, that is a concept which we are going to use now. So, let us choose which that ray is. So, if this angle has to be the smallest, you know that this angle has to be the largest, and the reason why I am saying that is we know A is equal to R1 plus R2, correct. So, if R2 has to be the smallest, then because R1 plus R2 is a constant, this is constant. So, this has to be smaller, which means R1 has to be larger. So, if R1 has to be larger, when will that happen? This will be larger if angle of incidence is the largest, clear. And what is the largest possible angle of incidence that the light ray can have? It is 90 degrees. So, which means out of all the rays which I have here, I would be considering that light ray which has the maximum angle of incidence. Clear? So, if I draw that light ray here, so this is what that light ray would be. So, this is the light ray which I have to choose, and this light ray enters into this medium in this manner, and if that light ray is getting reflected back, we can say that every other light ray, if the light ray is incident like this, like this, like this, so every other light ray will definitely get reflected back. Clear? So, that is the concept. So, I'll tell you again. So, this is the largest angle, correct, which means this is the largest possible value of R1, which means this will be the smallest possible value of R2. So, for this smallest value, if TIR takes place, for any other value of incidence, TIR will definitely take place. Clear? So, let us write the condition for that. So, we now know that here, let us say the refractive index of this is some mu. We need to write the condition here. We need to find the relation between mu and A, such that no light ray will come out of the second surface, correct? Okay. So, if light ray is incident at 90 degrees, we all know that it enters into the second medium at an angle of theta c, correct? So, it enters into the denser medium at an angle of theta c. Now, if this is theta c, can you tell me what this angle would be? How much would this angle be? So, this angle would be A minus theta c, correct? Because this plus this should be equal to A. So, now writing the condition is pretty simple. So, this is A minus theta c, and what is the condition we write for TIR? Angle of incidence should be greater than critical angle. So, angle of incidence is A minus theta c. So, that should be greater than theta c. So, that is it, that would be the condition for TIR, but we need to find the relation in terms of mu. So, I will rearrange this in terms of mu. So, solving this will give me theta c, 2 theta c is lesser than A, or theta c is lesser than A by 2, and taking sine on both sides, I get sine theta c should be lesser than A by 2. I mean sorry, sine A by 2, correct. So, it should be lesser than sine A by 2. So, you know that sine theta c is nothing but 1 by mu. So, if you replace that with 1 by mu, what do you get? The final result that I am going to get, I will write it down here. So, that would be 1 by mu lesser than sine A by 2, and simplifying this would give me mu greater than cosecant A by 2. So, this is the condition for which no light ray will come out of the prism. So, any light ray, you can make sure that the light ray is at any angle, clear. So, none of the light rays will be able to come out of this surface if this condition is satisfied. So, that is what we mean by the condition for no emergence, clear. So, please understand that. So, whenever they are asking you to find a condition for such scenarios, so choose one particular ray such that if you write the condition for that, then every other light ray will also satisfy, right. So, that is the idea. Okay. So, now after this we will discuss about the concept of deviation produced by a thin prism. Deviation produced by a thin prism, right. So, thin prism basically means that the angle of prism is a very small value. So, if I consider a prism in such a way that this angle A is very small, then that is what we mean by a thin prism. So, it would be something like this. So, it should not be even the value, I mean the angle which I have drawn here is also sufficiently large. So, that is just for your understanding. So, think that this angle is very small, generally around 5 degrees or 6 degrees or something like that. So, such kind of prisms are what we call as thin prisms. So, this is just for your understanding, clear. So that I will be able to draw the diagram. Okay. So, now we are going to find out what is the deviation that this thin prism produces for a light ray which is incident on it. So, in this particular case, let us say the normal to this will be something like this, and if there is a light ray which is incident in this manner, so at an angle of I. So, we know that this light ray will enter into the second medium. It enters like this, it will be making an angle over here, and the value of that will be R1, and this would be R2, correct, and eventually the light ray will come out. So, this is what happens, same as the earlier case, but like I told you, because the prism is very small here, the angle of prism is very small. So, we can make some approximations here, and after making the approximations we will be getting the result, right. So, we will see what that is. So, we know that this is I and this is R1. So, basically there are two refractions that are occurring here, one at this surface and the other at this surface, and because angle of prism is very small, right, and R1 and R2 values also are very small, we can consider that the light ray which is incident will also be at a very small angle. So, whatever we are writing here, the condition which I am writing here is for angle of incidence which is very, very small. Now, keeping that in mind, keeping in mind that I, R1, R2, E, although I have represented E to be a larger value, consider that E is also smaller. So, all these would be very small angles, keep that in mind, right. Okay. A is also small. So, if I write Snell's law at this surface, at the first surface, I can write 1 into sin I is equal to mu, let us say the refractive index of this is mu into sin R1, correct. Now, once again I am reminding all the angles which you see here, I, R1, R2, E, A, all these are very small angles, which means I can make approximations. Sin I can be written as I, sin R1 can be written as R1. So, from here I can write I is equal to mu R1, right. Similarly, here I will be writing mu times sin R2 is equal to here 1 into sin E. So, from here I can say once again, if I approximate, sin R2 is R2, sin E is E. So, mu R2 is E. So, mu R2 is equal to E. So, now let us write the expression for deviation. Now, if you see here, you know, whenever refraction takes place, so if I have light which is incident in this manner, I, so if it is entering into a denser medium, it bends towards the normal and the angle would be R. So, what is the deviation that it experiences? I will be like this. So, it bends and it makes an angle of R. So, you know that the deviation that it experiences is I minus R, correct. So, the deviation that the light ray experiences here would be I minus R. So, if I write that I minus R1, correct, plus, now it is experiencing a deviation on the other side also, clear. So, on the other side if you see that is travelling from a denser to a rarer medium. So, here you can observe that if this is the surface and if this is the normal. So, yeah, light ray is incident at R2 and it is coming out at E, right. So, which means the light ray is travelling like this, but eventually it is turning this way and coming out. So, in this case E is greater than R2. So, what will be the deviation that it experiences there? So, that would be E minus R2. Remember, in both the cases at this surface as well as this surface, we have deviation happening in the same sense. That is why I wrote a plus sign here. You can observe this, in this particular case it was going like this, and because this is denser medium it bends towards the normal, right. So, it is going like this now, and here it is going like this, but because it is entering into a rarer medium it goes away from normal, right. So, in both the cases the deviation is clockwise. So, that is why I have added, clear. So, this will be equal to I plus E minus R1 plus R2. We already know that R1 plus R2 is nothing but A, correct. So, this is A minus I is mu r1, E is mu r2. So, if I substitute, I will get mu times r1 plus r2, and r1 plus r2 is once again A. So, if I take A common, I would be getting this as A into mu minus 1. So, that is the deviation that is produced by a thin prism. And one important thing you will have to keep in mind regarding deviation produced by a prism is that a prism deviates a light ray towards its base, towards its base. So, now whatever I have written here is considering that the prism has a higher refractive index than surroundings. So, if I consider that the surroundings is air and the prism has a higher refractive index. So, in such a scenario, which is most of the cases, the scenario would be like that, correct. So, outside we have air and the material of the prism would be higher refractive index. So, in such a scenario, we can say that the light ray deviates towards the base of the prism. So, you can keep this in mind, and if it is placed in a medium of a different refractive index, which is surroundings having higher refractive index, then it would be the opposite, right. So, this is the idea, this is a very important result. So, this is the deviation that is produced by a thin prism, right. So, students, now we will discuss about something called as Cauchy's relation. So, till now we have a basic idea that whenever we have a light, let us say which is passing through air, so we can say that refractive index or the speed of this particular wave will depend on which medium the wave is travelling, correct. So, if it is entering into a medium having a refractive index of mu, so if the speed of that in air is c, it immediately becomes c by mu, right. So, we know that as medium changes, the speed of light changes, and based on that we define the refractive index. So, what Cauchy's relation states here is that if I consider a medium and if different wavelengths of light are passing through that medium, let us say if this is lambda 1, this is lambda 2 and this is lambda 3. So, Cauchy's relation basically tells us that this particular medium offers different refractive indices for different wavelengths of light. So, not all these wavelengths of light travel with the same speed, clear. We have not learnt about this till now. So, we have considered that the speed of light in the surrounding, if in air medium, if it is c, the refractive index in this medium is c by mu, right. So, that is what we have discussed till now, but Cauchy's relation is something which we have not applied yet. So, what it states is that there will be a small variation in the refractive index of this medium for different wavelengths of light, clear. So, that is what you should understand. So, refractive index is not a fixed value for any kind of light, right. So, for a particular light it could be a value, the same medium could offer a different value of refractive index for a different wavelength of light. So, what is that relation is what we call as Cauchy's relation, right. So, it is something like this, the relation is like this. So, mu of lambda means mu as a function of lambda can be written as a plus b by lambda square plus c by lambda power 4 plus so on, right. So, that is the expression, and a, b, c are constants, a, b, c are constants. So, by looking at this you can get an idea that as the value of lambda increases, the wavelength or the refractive index that the medium offers to that particular wavelength will be lesser, clear. So, you can say that a, b, c are constants which depend on medium. So, which depend on medium, right. So, I am not changing the medium, the same medium. So, we can't define a particular value of refractive index for this medium. So, because this medium offers some mu 1 for this light ray, it offers mu 2 for this light ray and it offers mu 3 for this light ray. It can offer different refractive indices for different media. So, that is what this concept basically means, clear. So, like I told you, for higher lambdas mu is lesser, right. So, if I actually plot a graph of whatever expression that I have written here, so this is actually so on, but we can neglect the terms after this. So, these terms C, D, E, all those terms can be neglected because the powers become very large and the C, D, E, the numerators, the constants will also be very small. So, you can actually neglect this complete part and you can actually understand this as mu is equal to A plus B by lambda square. So, this is the expression which determines the refractive index that a medium offers to a particular wavelength of light, and the graph would be something like this. The graph is between mu and lambda. So, it is like this. So, it becomes constant at a particular value. So, as lambda becomes very large, you can see that the refractive index becomes a constant value. It does not change much for higher lambdas, and what is that value? A. That constant is A. As lambda tends to infinity, the value of mu tends to A. So, that is why we have this horizontal line drawn there, and as lambda tends to 0, we can say that mu tends to infinity, clear. So, that is the basic idea. So, you just understand the graph, and the most important thing we need to know here is they will not be asking you many numerical questions based on this, but the relation is the important. By relation I mean how does it depend on lambda. If lambda increases, what happens to mu? If lambda decreases, what happens to mu? So, that is something which you will have to definitely keep in mind. So, if you remember this, that would be enough. So, if lambda increases, mu decreases, clear. So, based on that, see, whenever we consider light, so whatever light which we use, the light coming from, let us say any tube light or even the light coming from sun. So, you know that that is not just one single wavelength, right, it is a spectrum, right. Even if I consider white light, so you know that white light basically means a combination of many colors, right, many wavelengths, right. So, of which we generally represent VIBGYOR. So, we generally represent VIBGYOR as the basic fundamental colors in that, right, wavelengths. So, even if I consider V, I, B, G, Y, O, R different wavelengths, you know that because the wavelengths are different, they have different refractive indices when passing through a medium, yes or no. So, when these wavelengths or when white light is incident on a particular medium, so the individual waves in that particular white light travel with different velocities, clear, they experience different refractive indices, and that is the reason why, see, we discussed this earlier, that when I consider a prism, so when we consider a prism and if light is incident on this prism, see, if it is a monochromatic light, which means a single wavelength, then there is no problem, the light ray bends and it comes out, it just experiences a deviation. But if the light ray which is incident is white light, so white light means what? It contains all these individual wavelengths also. So, as I told you, for example, if I consider that this is glass, which usually what prism is made of. So, when white light is incident on a prism, now observe carefully. So, this contains different wavelengths and this medium offers different refractive indices for different wavelengths. So, which means, so out of these VIBGYOR, each and every one of them will deviate by different angles, right. So, if this was the initial direction, so what you would observe is that by the time the light rays come out, because of the difference in refractive indices of each and every color experiences different refractive indices, clear. So, different colors will experience different deviation. So, as a result of that, you would observe the light rays coming or deviating by different angles in this manner. So, this is what you would observe eventually. So how many are there? 1, 2, 3, 4, 5, 6, 7. Yeah. So 7. So can you guess if let's say these are VIBGYORs, the 7 wavelengths which are coming out. So which of these will have the highest deviation? Highest deviation corresponds to this one, correct? And this is the one which corresponds to the least deviation. So out of these, which will have the highest deviation and which will have the least deviation, right? So we can actually understand that by a simple logic. We can use the concept of deviation in the case of a thin prism. So the deviation produced by a thin prism is mu minus 1 into A. Although it is not a thin prism, we can say that whatever deviation that thin prism does, even a normal prism also follows the same pattern, correct? The magnitudes might be different, but the pattern would be the same. So if I use the formula which I know for thin prism, which is mu minus 1 into A, from this I can understand that delta is higher if mu is higher, correct? Now we already know that for mu to be higher, wavelength has to be lower. So if mu is higher, which implies from Cauchy's relation, when will mu be higher? When lambda is lower. Lambda is lower. So it basically means that out of all the colors, the one which has the least wavelength has the highest deviation. Now you know which has the least wavelength out of VIBGYOR, which has the least wavelength, which is the most energetic? Violet, right? Least wavelength means more energy. So this is the one with the least wavelength and R is the one with the highest wavelength. So you can understand that wavelength increases in this direction, lambda increases. So keep that in mind, right? So V is the one, violet is the one with the least wavelength. So least wavelength corresponds to highest mu, which will also imply higher deviation. So what we would observe here is that as white light is incident on a prism in this manner, then the one with the highest deviation would be violet, right? The one with the least deviation would be red, and rest of the colors would be somewhere in between them. So we can say that V, I, B, G, Y, O, R. So we will be from bottom to top, right? Violet deviates the most. So we can say that the deviation experienced by violet ray will be the refractive index of violet minus 1 into A, considering that it is a thin prism. If I consider that it is a thin prism, you can't apply that for any random prism with greater A values, right? And in the same thin prism scenario, if I write for red, we can write it as mu R minus 1 into A. Clear? Okay. Now that we have understood that different colors of light will have different refractive indices, although the difference is not very much, but there will definitely be a difference. Okay. See, for example, earlier throughout the discussion, we have understood that the refractive index of glass. So when I say refractive index of glass is 1.5. So we have been using this result, we have been talking about it. So when I say refractive index of glass is 1.5, so whose refractive index is that? I mean, is it the refractive index of violet? Is it the refractive index of red? No. So this represents the mean refractive index, mean in the sense average. So this represents average refractive index. So what we have been using till now is the average refractive index offered by the medium for white light. Clear? So average refractive index, and by definition we can say that average refractive index, average mu, is the mu experienced by, is the mu experienced by which light? That light should definitely be somewhere in between. If I am considering mu as the average mu of different waves, I mean different wavelengths out of these 7, then the average mu should be somewhere in between, right. So, yeah. So, average mu is the mu experienced by yellow light. So, this is what we have been discussing till now, all the values which they state. So, the refractive index of this medium is something. So, they are basically referring to the refractive index experienced by yellow light, or you can say that that is the average value of refractive indices experienced by the whole spectrum, clear. So, that is the basic idea. So, keep that in mind. So, violet is the one which deviates the most and red the least, clear. And this phenomenon of, you can see here that because of the concept of different deviations, the light ray is spreading, the light ray is dividing into different colors. So, this phenomenon is what we call as dispersion. So, whenever we pass white light through a prism, so as white light enters a prism, it comes out as different colors. You would have seen this in lower classes also, you might have done some experiments with prism, right. So, that is the idea. So, students, now let us solve some examples. So, here they are asking, draw the path of the different colored light if angle of incidence is equal to the critical angle of green light. So, the angle of incidence that they have given here I. So, they are saying that that is equal to the critical angle for green. So, which will mean that here, because we have white light. So, white light is a combination of all 7 colors, if I consider 7, right. So, because the angle of incidence is the theta c for green, can I say that green light will travel along the interface. So, this is how green light will travel, right, it grazes the surface. Now, we have others. So, we have VIP GR. Okay. So, we need to now understand what happens to VIB and what happens to YOR. We know that G travels along the interface. So, I would suggest you pause here and think about this scenario. So, I will definitely tell you that one group of this out of these two, let us say this is one group and this is the other group. One group undergoes TIR and the other group will refract into the next medium. So, I want you to think about which group will reflect, which group undergoes TIR and which group will refract into the next medium. So, obviously, this is the denser medium and this is the rarer medium. Okay. So, think about that, right. So, let us see. So, to understand which ones will undergo TIR, first I will need to know the critical angles for each and every light ray, correct. So, for green, this is the critical angle. So, let us see what the critical angle for different colors of light is. So, we know that critical angle can be given by 1 by sin theta c is equal to 1 by mu, considering that this is the rarer medium is some air. So, if I consider this is air, I can write critical angle as 1 by mu. So, which means, observe carefully, if mu is greater, theta c is lesser, correct. So, if mu is greater, theta c is lesser. So, out of all the colors which I have, which one has the highest mu? Violet. So, violet is the one with the least theta c. So, we can say that violet has the least critical angle, correct. So, now you can easily guess. So, can I say that because G has this much critical angle, so VIB, all of them have lesser wavelength, or we can say higher mu than G, correct. VIB. So, we can say that if I write a relation like this, so mu decreases in this direction. So, if mu decreases in this direction, we can say that theta c increases in this direction, correct. We can't say they are inversely proportional, but this is the relation, correct. So, if mu decreases like this, then theta c increases like this. Now, you know we have been using this concept every time. So, the chances for TIR to take place will be more if theta c is less, correct, or think of it like this. Let us just understand this by using some values. So, let us say VIB GYOR. So, let us say green has a critical angle of some 40 degrees and violet has a value of some 30 degrees and this red has a critical angle of 50 degrees, correct. Now, think of this scenario. The light ray is incident at 40, light ray is incident at 40. Now, what happens to violet and what happens to red? Let us just check for those, because this whole group behaves in the same manner, this whole group behaves in the same manner, right. So, VIB. So, if I look for violet, we know that violet has lesser critical angle. So, which means if violet light is incident at 30, it will graze the interface. That is what critical angle means, correct. But the light ray is incident at 40, which is the critical angle for green, correct. So, if it is incident at 40 and violet has a refractive index, critical angle of 30, what will happen to violet? Violet will reflect back, not just violet, V, I, B, all the three will reflect back, because all these three will have lesser critical angle than 40 or than the critical angle for green. So, let us just take these values itself. So, if this is incident at 40 degrees, so all these three will have a critical angle of, let us say 35, 36, 38, something like that, and for all those three lights we can say that this angle of incidence is greater than their theta c. So, they will reflect back. So, what I can say is one group will get reflected back in this manner at the same angle. So, this light ray which is coming out will contain all the three, VIB will all be present in this reflected ray. So, all the three will combinedly get reflected, right. Now, if I talk about YOR, yellow, orange, red, they will definitely enter into the next medium, correct. So, will they also go in a group? Will all the three YOR go as one single beam? No, because that is refraction. Reflection has to happen in only one manner. Whatever is this angle, same will be this angle, correct. But refraction can happen in different ways. So, we can say that they go at different angles, and you can just easily say that VIB GYOR, YOR. So, that is how the refraction occurs in this particular scenario, clear. So, we can say that red has the least probability out of all the VIBGR to undergo TIR, and violet has the highest probability to undergo TIR. So, chances for this to undergo TIR are greater. I will write it down as well, you can note it down. So, chances for TIR to take place is highest for violet and it is the least for red, clear. So, that is the basic idea. So, please understand this, see this, as long as you know that this concept can be logically understood. So, you can connect all these, you will have to connect wavelength with mu first, mu with theta c first, and then the concept of critical angle, clear, or total internal reflection, right. So, now let us see another question. So, here they are asking us to find the net deviation experienced by the light ray. So, this is the incident light ray. So, it strikes a thin prism. So, the angle is 6 degrees, the refractive index of this prism is 3/2, and so it strikes the prism, it comes out of the prism. So, let us say this is a ray which is horizontal. So, this is horizontal. So, it is incident horizontally onto that prism, right. So, it strikes the prism and it bends, right, the light ray undergoes some deviation. We know the formula for calculating that deviation also. So, it undergoes a deviation, it strikes the mirror like this, and because of that it once again deviates, reflects back from the mirror, and it passes through the prism and once again deviates to the prism. It passes through the prism twice. So, it deviates twice because of prism, right. So, let us see it step by step. We know that whenever a light ray is undergoing such successive steps, we will have to analyze one by one, right. So, first as it passes through, this is the initial direction of the light ray, we can say that it bends, it deviates by some angle, correct. So, let us calculate what that angle is. So, the formula which we have is delta is equal to mu minus 1 into A. So, mu 3 by 2 minus 1 is 1 by 2 into A is 6 degrees. So, solving this will give me the value as 3 degrees, right. So, this angle here will be 3 degrees, and remember, write the sense as well, because we have 3 successive deviations happening. So, it is better we write the deviations every time. So, which sense is this deviation? We know that light ray always bends towards the base of the prism, right. So, it bends like this. So, this is clockwise, right. So, 3 degrees clockwise, correct. Okay, now it is striking the prism, plane mirror. Can I say that if this angle is 3 degrees, this angle here will also be 3 degrees, the angle of incidence for the mirror is also 3 degrees, clear. So, that would be 3 degrees, which means after reflection the light ray strikes like this, it reflects and it strikes the prism in this manner such that this angle here is also 3 degrees. So, this is the first. Second, it is undergoing reflection from the mirror, due to which we can write the expression for deviation as, what is the formula for that? Pi minus 2i, right. So, 180 degrees minus 2 times I is 3. So, solving this will give me 180 minus 6, 174 degrees. Now, clockwise or anti-clockwise? So, see that. So, this is the initial direction of the light ray. The light ray was going like this and it deviated like this, correct. So, from this direction the light ray deviated to this direction. So, light ray bent like this, clear. So, this is the deviation. So, this means clockwise. So, this is also clockwise. Okay. Now, the last step. So, this was the initial direction of the light ray and eventually it bends towards the prism, because that is what, towards the base of the prism, that is what the prism does, it bends it towards the base, and we know the deviation that the prism produces. So, in the third step it experiences a deviation of mu minus 1 into A, I have already calculated that. So, 3 degrees. Now, what is the sense here that you should be very careful. So, the light ray is travelling like this. So, do not think that initially it produced clockwise deviation, now also it will be clockwise. So, see here, so light ray is travelling like this, it bends towards the base, which means it bent like this, right, from top to bottom, and this sense is anti-clockwise, correct. So, this would be 3 degrees anti-clockwise. So, we have 3 deviations, just find the net deviation. So, net deviation will be this and this will get cancelled out and we will be left with this. So, 174 degrees clockwise, right. So, that should be the answer. We will see few more. So, students, here in this question it is given when I is 25 degrees, E is 47, which is emergence, and the deviation is 32 degrees, right. And if delta minimum occurs when I is equal to 33 degrees, find delta minimum. So, that is what they are asking. So, we have a prism. So, using the given information, they have basically given in a particular scenario, the value of I is given to us, the value of E is given to us, right, even the deviation is also given to us. So, from using that information I can directly calculate the value of A. So, because I know that the deviation value is nothing but I plus E minus A, correct. So, if I substitute, I would get 32 degrees is equal to I is how much, 25 plus E is 47 minus A. So, simplifying this would give me 60 plus 12, 72. So, this is 72 and this is 32. So, 72 minus 32 is 40. So, the angle of prism is 40 degrees, right. Now, in the second case, so this is case 1 and this is case 2. So, in second case what they are doing is they are telling us that minimum value of deviation occurs when angle of incidence becomes 33 degrees. Find delta minimum. So, we know that delta minimum is nothing but I plus E minus A once again, but in the case of minimum deviation we know that I and E should be same, correct. So, which means whatever is the value of I that they have given is also the value of E. So, I can directly write 2 into 33 degrees I plus E minus, we already found the value of A as 40 degrees. So, that is it. So, this is 66, right, yeah, 66 minus 40. So, 66 minus 40 would be 26 degrees. So, that is the minimum deviation, clear. So, now let us see this. So, here they are saying they have given us a scenario, a combination of 3 prisms and all the 3 prisms are right angled prisms. So, angle of prism is 90 for all the 3, clear, and it is given that a light ray is incident in a grazing manner on the first prism and it comes out in a grazing manner on the third prism, right. There are 3 prisms, this one with refractive index mu 1, this with mu 2, this with mu 3, all the 3 are right angled prisms. So, now we need to find the relation between mu 1, mu 2 and mu 3 for the given situation to occur, right. So, let us write the equations. We know that it is grazing incidence here and it is grazing emergence here. See, I have told you all we will have to do in such cases, all we can do in such cases is just write Snell's law, right. So, that is what we can do. So, I will write that. So, let us say this light ray travels in this manner. So, something like this, and after this it bends something like this, and after this it bends something like this and it comes out. Let us just take a scenario like this. So, this is the path followed by the light ray, clear. So, let us write Snell's law. So, I will assume that it enters into this medium at an angle of theta 1, it strikes the second surface. We know that this is 90, if this is theta 1, how much should this angle be? So, we know that this plus this should be 90, correct. So, this would be 90 minus theta 1. Now, I will assume it enters into the second medium at an angle of theta 2, clear. So, which means here it strikes, if this is the normal. So, what would this angle be? Once again the same logic, because this is just a prism which is inverted. So, we know that this angle with the normal plus this angle with the normal is 90. In the same manner, this angle with the normal and this angle with the normal should add up to 90. So, if this is theta 2, then this would be 90 minus theta 2, correct. Similarly, if it enters into the third medium at theta 3, this angle would be 90 minus theta 3. So, we will write Snell's law. So, we can write Snell's law here, Snell's law here, Snell's law here and here. So, we have 4 equations of Snell's law which we can write. So, let us do that. So, if I write Snell's law here, so we can say 1, this is 1 into, yeah, this is air, right, even the angle of incidence is also 90 degrees. So, 1 into sin 90 which is 1. So, 1 is equal to mu 1 sin theta 1, mu 1 sin theta 1, correct. Similarly, here if I write Snell's law for this surface, so what do I get? So, in this particular scenario we have mu 1 into, this is the angle of incidence at this surface. So, mu 1 into sin 90 minus theta 1. So, I can write mu 1 into sin of 90 minus theta 1 is equal to, here for this I can write mu 2 into sin theta 2, correct. Similarly, I will write here now. So, the angle of incidence is 90 minus theta 2. So, I can write mu 2 sin 90 minus theta 2 is equal to here mu 3 sin theta 3, right. And finally, at this surface I can write mu 3 into sin 90 minus theta 3 is equal to, it is entering into air at an angle of 90. So, it becomes 1, mu is 1, sin 90 is also 1. So, yeah, so we have 4 equations, and you can eliminate theta 1, theta 2, theta 3 from these 3 equations, I mean from these 4 equations, and you will be finally left with the required result. So, how do you eliminate theta 1, theta 2, theta 3? Yes. So, we know that this is sin theta 1 and this is cos theta 1, and I can use the idea that sin square theta plus cos square theta is equal to 1. So, using this identity, I can eliminate theta 1 and theta 2 from each of these equations. So, let us see how to do that. I will square this. 1 is equal to mu 1 square sin square theta 1. I will rearrange this, I will take this on this side, this on that side, right. So, I will be getting mu 2 square into sin square theta 2 is equal to, this is cos theta 1, correct. If I square and take it to the other side, that would be mu 1 square cos square theta 1, right. Similarly, here, so we have theta 2, so I will leave this theta 2 term on this side itself and write the equation. So, if I square it, I get mu 2 square, mu 2 square into, this is cos, right. So, cos theta 2 whole square. So, which is cos square theta 2 is equal to, square this, mu 3 square into sin square theta 3, right. And finally, because we have theta 3 on that side, I will square this and take it to the other side. So, I will get 1 is equal to mu 3 square cos square theta 3, mu 3 square cos square theta 3. So, that is it. So, now you can easily say that when I add the terms, theta 1, theta 2, theta 3 will get cancelled out. So, when I add these two, this plus this will become mu square. So, on the left hand side we have 1 plus 1 plus mu 2 square, which is 2 plus mu 2 square is equal to, on this side we have, so these two when added, these two terms when added gives you mu 1 square, these two terms when added gives you mu 3 square. So, on this side we have mu 1 square plus mu 3 square. So, this is the final condition that should be satisfied, that should be present between mu 1, mu 2 and mu 3, such that this grazing incidence and grazing emergence scenario can happen. So, that is it, students. With this the concept of prism comes to an end. So, in the next class we will talk about refraction at curved surfaces, and once that is done we will be starting with lens, right.